In this video lecture, I will introduce and discuss the trapezoidal approximation technique to find approximately the value of definite integrals. And previously we have learned the left endpoint approximation, right endpoint approximation, from which we also derived the midpoint approximation, and now we'll talk about another way to approximate definite integrals called trapezoidal approximation. And the idea is very simple. If we take the same problem, let's take exactly the same problem, but instead of M4, now let's use T4 to approximate this integral. And here's what's going to happen. Actually, let me take this one. So let's discuss what it means to find T4. And surprisingly, T4 is very easy to compute if you already have L4 and R4. And let me show you how. T4 is simply the average between L4 and R4. And if you already know L4, which we do, we computed it earlier, it is 0.8220. And if you know R4, which we do, it's 0.6640. If we find the average of these two, we get 0.743, which is, if you compare it to the actual answer, which I have over here at the bottom right corner, you'll see that the average of the two is actually a pretty good estimate. But the question is, why is it called the trapezoidal approximation then, if all we're doing is finding the average between the left endpoint and right endpoint approximations? And the answer is in geometry. When you're looking for the average area of two rectangles that look like this, for example. So if we take the average of the two, I guess I should finish drawing the purple one. So what would the average area of these two rectangles look like? Well, it's going to have everything that orange rectangle has, right? Plus it's going to have half of the difference of the orange and the purple rectangles, and half of the difference can be expressed geometrically like this. So if we add the yellow and the purple areas together, as a result, we'll get this area that I'm shading right now in white color, which is the area of this exact trapezoid. So the bottom one represents the left endpoint approximation, the top one represents the right endpoint approximation, and the average of the two presents the area of the trapezoidal. It's the area of a trapezoid, but which we'll refer to as a trapezoidal approximation. So if you already have Ln and Rn, you can easily find Tn by doing this. Now, what if you don't have Ln and Rn? Then how do we find this area? Well, then we'll have to look at what is L4 and R4. And L4, it's the sum, if we recall the formula, it's the f of, in this case, it's f of x0 plus f of x1 plus f of x2 and plus f of x3. But R4, if you remember, it's actually the same exact thing, except we start with f of x1 and go all the way until f of x4. And then we multiply it by delta x. Right, so frequently what we do is we shorten this notation and we write the formula for t. Well, let me write it first for t4. It will be, so we usually carry 1/2 to the front, so instead of dividing by 2 we just write 1/2, and then you know how we had f of x1 plus f of x2 plus f of x3. Actually, I messed up. We should have f of x0 first. And then these are going to repeat, so instead of repeating them, I'm actually just going to multiply it by 2, and then I'm going to add the last one that doesn't repeat. So in our case, it will be x4 and then we multiply it by delta x. And again, frequently, just to make it easier to remember, we don't put this parenthesis inside of the parenthesis, we just double every entry inside of those parentheses. So in general, the formula for Tn can be written like this, as 1/2, and here we're going to have f of x0 plus 2f of x1, and of course, to be fully complete, I have to put stars over here. Actually, no, hold on, no, there's no stars here, right? So these are the partition of the interval, so I don't need no stars over there. And this is what a formula would look like. Why do we prefer this formula to be written like this instead of sigma notation? Because in sigma notation it will be really hard to come up with this general formula. However, it's not a bad thing in this particular case, because in the near future we're also going to learn the Simpson's approximation. And in Simpson's approximation, we're also going to struggle writing it in a sigma form. So the formula for the Simpson's approximation would look a lot like this, right? So it's not a bad thing. And let's try to apply this formula on this problem. So A is 0. B is 4, N is 4, delta x is B minus A over N, which is 1, and therefore we're going to have an interval from 0 to 4, and we're going to divide it into 4 subintervals, and each one of width 1. So we can easily figure out this partition. It's going to be 0, 1, 2, 3, 4, and we're going to have some function here. And again, we're not looking for, we don't really care about what the function is, because we understand the process. So T4 will be 1/2, it would be f of x0 plus 2f of 1 plus 2 f of 2 plus 2 f of 3, and the last one is f of 4 by itself, and we're going to multiply it by delta x is also 1. So again, what we did here is we kind of drew out analytically these trapezoids. That's what we did, and we're looking for the area using this method. So I'm going to use Desmos to find the values of this function at these points. So I'm going to define a function 3x squared over x plus 2 on the interval from 0 to 4. This is what it looks like. Alright, so it's an increasing function, and I'm gonna need this table of inputs outputs. So we're gonna plug in all this 0, 1, 2, 3, and 4. Should take a screenshot of that. Delta x is 1, so makes it a little easier. And finishing it off, so we have 2 plus 6, 8, 8 plus 8, 16, 16 plus 10.8 is 26.8, and we need divided by 1/2. So the answer is 13.4, whatever the units squared in this case, and that's how we use the trapezoidal method to estimate the definite integral. Now we did it kind of analytically here using the process. Now let's try and do it geometrically, I guess, and let's take a look. So given the graph of a function below, approximate the area under the curve. And let's see. So our A is 0, B is 3, delta x is B minus A over N is also 3, so it's 3 minus 0 over 3 is 1, and we're gonna go from 0 to 3, and geometrically this is what it's gonna look like. We're gonna have this trapezoid, then this trapezoid, then this trapezoid. So we can look for the area of those trapezoids geometrically. However, if we do it analytically, it seems like it would be much easier. So T3 will be equal to 1/2 f of 0 plus 2 f of 1 plus 2 f of 2 plus f of 3 times delta x. And from the picture we can figure out all the ingredients here. So f of 0 is 5, f of 1 is 8, f of 2 is 3, and f of 3 is 4. So the final answer is 16, 21, 27, 31. So it's 15.5 units squared. Yeah, it seems like we covered the trapezoidal approximation, the formula, and how to use the formula when the function is given or when the graph of a function is given.